Hello, everyone. Welcome back to Global Math Mentor. This is A level 9709 Pure Mathematics 3, and the topic I'm going to discuss is complex numbers. Before we dive into the topic, I want you to pause the video and quickly try to solve this equation. X squared plus 1 equals to 0. So what just happened? X squared equals -1, and when you square root it, you get a math error. Oops, that is not a solvable case. Earlier mathematicians were not able to solve these kind of equations, but thanks to this fascinating field of mathematics known as complex number, we can now solve equations with imaginary roots. Let's call this square root -1 a value, an alphabet I, which is iota. Iota is just a symbol used to represent this number, and this number has a name. We call it imaginary number. So that's the beginning of this concept. Any number which has this form, let's say Z is the complex number, and A plus IB. So this IB is known as I is the imaginary number, B is the imaginary part, A is the real part. So I know it sounds confusing, but grab on your notebooks and let's write some notes. So A is known as the real part of this complex number. B is known as the imaginary part of this complex number. I, we already know, is the imaginary number. So, example of some complex numbers. Let's say 3 minus iota. That's a complex number. If I say it's U, or I can say W, like half plus √3/2i. All such numbers, or even let's say V is a complex number, -7 iota. So these are the examples of these complex numbers. There's much more to it. Let's see. So let's take a look at what is required in this topic. So that's the first idea. Understand the idea of complex number. Recall the meaning of the terms real and imaginary part as already discussed in the introduction. So if a complex number Z is A plus IB, we know that A is the real part, but these notations, look at this thing. These notations are very important. All right. So what is this IMZ and REZ? REZ stands for real part of Z. So this A has a notation now. And similarly, IMZ is known as the imaginary part of Z, and this is B, this number over here. And this is important. Note very well that A, B itself belong to the real numbers. Okay, now this is an interesting point as well. You used to think that real numbers are the greatest possible group of numbers, like the largest continent. Every number is a subset of real numbers. But now we look at another system, which is imaginary numbers. And believe me, that complex numbers are even a greater group. And real numbers can be considered or are the subsets of complex numbers, right? I, we already know its value is square root of -1, which is the iota, the imaginary number. All right. So any complex number can be written like this. Keep in mind, you're familiar with the notations like real of Z, imaginary part of Z, imaginary number, and the form of the complex number, right? Okay, so next we look at what are these things, this modulus, this argument, this conjugate. So there are so many things, so I'll go step by step, okay? So first, I will tell you like what is a modulus of a complex number. Modulus. Fancy term. If you have studied the unit vectors in your O levels or IGCSE or even A levels, you know this that there is a thing vector and there is the magnitude of a vector. So just consider that every complex number, now mark my words carefully, note it down somewhere, can be regarded as a position vector. All right. And there is a special kind of a diagram on which we represent these complex numbers. That is known as the Argand diagram. So, students, there's plenty of information, and I don't want you to miss out on any of that. So, whatever I'm giving you the ideas, just box them so you can highlight each of them and remember them in your notes as well. So, this is known as the Argand diagram. So, not a big deal. Argand diagram is not like a different thing. It is like an XY plane. But in this diagram, the x-axis has a name. We call it the real axis. And similarly, the y-axis has a name. We call it the imaginary axis. And any coordinate that you see on this diagram, for example, if you see a 2, 1, remember, it's not a coordinate like a Cartesian coordinate xy. This is a complex number where the real part is 2 and the imaginary part is 1. So I can write, if this is, let's say, the alphabet W, this coordinate, I can write W as 2 plus iota, since the imaginary part is just 1 and real part is just 2. And AB are real numbers, but why do we call 1 the imaginary part? Because the coefficient I is there with that number. That's why. Otherwise, A and B are real numbers. I want you to pause this video and note down everything that I've written. Okay, so let's take a look at it. So now connect it with the idea of vectors. The length of a vector is known as its magnitude. Similarly, modulus is the length of this complex number on an Argand diagram, like how far it is from the origin. So that is what is known as a position vector as well. So the notation used for modulus is just sometime written as mod z, or you can write the same vector notation z and put this modulus sign, these bars on the sides of this alphabet z. So how do you find it? If this is considered a vector, you know that the vector's magnitude is the real parts, like the x squared plus a y squared. So we will do a squared plus a b squared and square root it, right? Is anyone noticing that I haven't picked that I value over there? Remember, if you square I, you get a negative number, like a -1. Strange. That even that is also a condition why I is an imaginary number. Since I is a square root of -1, you square I, you get a -1. Have you ever seen any real number whose square is a negative number? I bet you haven't. So that's why I is an imaginary number. So when you take magnitude, do not consider this I inside the square root, because that might lead to a negative value inside the square root. When you are taking the length, only square the real part, square the imaginary part, add them and square root them. So if you want to find, in this example, if you want to find W modulus, you will do 2 squared plus 1 squared and square root it. So the modulus is 4 plus 1, a root 5. So I can say that on an Argand diagram, this complex number has a length of 5, root 5, right? So let's take another example and I can give you like a proper question how it will be checked. Like, okay, example, find the modulus of u equals to root 3 minus I. Okay, that is a complex number. So if this question pops up, you know that modulus is the length, and length formula is like real square plus imaginary part squared, add them and square root them. So I'm going to do root 3 squared plus a -1 squared and square root it. So this will become, okay, let me just write the u and absolute sign, modulus sign as well. So 3 plus 1. So that is a root 4, and the answer is 2, right? Okay, now let's take a look at the word argument. What is argument? You see, it's written over here. We just discussed modulus. Just like modulus is the length of a complex number, argument is the angle that complex number makes with the positive real axis on the Argand diagram. Now you need to reverse, and I think you need to listen to this again. So let me take an example, the same complex number which I discussed earlier. Uh, let's call this W, which is a 2, 1. Okay. And I'm going to put this over here. Let me just zoom it so you can take a look at it, what's going on. So what is the angle this makes with the positive real axis, right? So I'm completing my Argand diagram, and watch out again. It's not a coordinate. Any point that you see on an Argand diagram is a complex number. So it's the triangle. If I complete it, this is the height, this is the base, and I need to get this angle. Remember from the trigonometric course that you used to calculate the basic angles. And then the principal angle was something which was anti-clockwise or clockwise from the positive x-axis. So you can relate this idea. So we had some relation with the vector course and now some relation with trigonometry. So find connections. All right. So the more connections you find, that's better. So you realize that it's not a new thing. You have done similar work before as well. So if you want to get this angle theta, that will be the inverse tan of a 1 divide 2. Now, I can give either my answer as degrees or radian, but most preferably in pure mathematics 3, the answers, if the angle system is not stated, you give your answers in radians. So my calculator is already in radians. Yes, it is in radians. So I will do shift tan inverse of 1/2. Okay, so let's see, what do I get? So my answer is 0.4636. So this is 0.4636. So I can give my answer correct to 3 significant figure in radian as this. So this is the angle this complex number make with the positive real axis. So mark it again carefully. Take your notes, because this is going to help us later when we study about different forms of complex number. So I will share few examples. In each example, I will find the modulus and argument of the complex number, right? All right, before I start solving these problems one by one, I want you to read this part as well. The argument of a complex number, okay, let me just highlight it from here. The argument of a complex number will usually refer to an angle theta such that, okay, what is this? Minus pi to pi. That is the restriction on the angle. So you'll see what do I mean by restriction. So, but in some cases, the interval 0 to 2 pi may be more convenient. But mostly, like 90% of the time in the exam question, you'll see that the range of angle theta is given within minus pi to pi. For considering that into mind, I will solve each of them for negative pi to pi, but give you a variation that what if there is no restriction on how to find the argument. All right. So let's dive into it. Okay, so they're saying in example 1, find the modulus and argument of the complex number. Okay, and this is 1 plus I. So let's first find the modulus. If I say modulus, that is Z mod, right? And that is real part squared plus imaginary part squared. And the answer is going to be root 2. Okay, that's it. And for the argument, there is a notation you can check given in the syllabus that is known as argz. So argz, ARG stands for the argument. And we just discussed that argument is the angle. So always make a diagram while finding the argument. Just a rough diagram. It shouldn't be like very neat and clean. There are no marks for the diagram. So 1, 1, that's the complex number. Complete the triangle like 1 and 1. And this angle over here, we don't even need the calculator. You know from the basic angle, like the special triangles or the unit circle, whatever way you want to learn these values, the arc of 1, like the tan inverse of 1, is a 45, or the pi over 4 radian angle, right? So that is my answer. So this complex number was in the first quadrant, so there was no change in the sign. So I'll share some more examples now where the quadrant is different. By quadrant, I means that what if it's in the second quadrant, or the third quadrant, or the fourth quadrant, right? Example 2. Find the modulus and argument of the complex number z equals to root 3 minus I. If you want to try it on your own, just pause the video and give it a go. Come back and check my work later. Okay, so z mod is the modulus, that is real part squared and the imaginary part squared. While finding the length, it does not matter in which quadrant does it fall. The same formula applies everywhere. So 3 plus 1 root, which is a root 4, and the answer is 2. Okay? But now the things get interesting because this is the fourth quadrant. Sketch this complex number and see root 3 to the right and 1 is with a minus, so this is the fourth quadrant. Complete the triangle. This is a 1, this is a root 3, this is real part, and this is imaginary part. So now we find argz by the tan inverse of 1 divided root 3. Well, this is also a special triangle value. So you know that this is, okay, I'll give you a special triangle. What does it look like? These are the special triangles. This is a root 3, this is a 2, this is a 1, this is 60, and this is a 30. So you can check out the trigonometric videos to find more about these special triangles. There's another one, but right now this can do the work. So you see the tan inverse, the opposite is 1 and the adjacent is root 3. So the answer is going to be 30, which is a pi over 6. But check, this is the fourth quadrant. And there are two possibilities. Now here, when I talk about the possibilities, if the angular range is given from minus pi to pi, so you cannot go anti-clockwise. Reason being that this is going to be 2 pi minus a pi over 6, which is 11 pi over 6. And it does not fall in the domain. Let me just make the domain. So if your domain is theta is within pi and greater than a minus pi, then this answer is not acceptable. But if your domain for the angles is from 0 to 2 pi, yes, now this answer is correct. So that's why if the question restricts you for the domain, then you can give the straightaway answer like, since it's a clockwise, so you can say that your answer is a negative pi over 6, because if the direction is clockwise, the answer is negative for the angles. And if the direction is anti-clockwise, your answer is positive. So both are correct. Both are correct answers, but it depends on the angular domain which is given in the question. Problem 3. Find the modulus and argument of the complex number minus root 2 plus iota. If you want to try it, go ahead. Come back and check my work later. So the modulus is z mod negative root 2 squared plus a 1 squared. So this will become a 2 plus a 1, which is a root 3. In order to find the argument, I need to check my quadrant. Can you identify the quadrant? If you have, that's great. Okay. So this is a second quadrant. Reason, your x is negative and your y is positive. So this is the point -2 and 1 on an Argand diagram. Get this angle and then we'll see how do we find the angle anti-clockwise or clockwise from the positive real axis. All right? So let's find the tan inverse of a 1 divide a root 2. Okay? Now this is not a special triangle value, so I need to check it. So I can use my calculator to get this value. Shift tan inverse 1 over a square root of 2. Okay. So that is 0.6155. 0.6155. So I can write it as, okay, let's keep it the unrounded one and I'll round the final answer. Now look at this. I'll show you on the diagram. You can either give your answer like this or this. But the A-level students, I highly recommend, listen to me carefully, go for the shortest possibility, right? So you should go anti-clockwise in this case, right? Reason being that I don't want you to mess up when they give you a domain like a negative pi to pi. If they give you a domain negative pi to pi, then the clockwise option is not valid right now. Okay, so let's do pi minus a 0.6155. Why did I subtract it from pi? Because I need it with the positive real axis. Okay, you can say x-axis, but in complex number, we call it the real axis. Okay, so I'll just do the shift pi minus the answer. And there you go, 2.526, 2.526 dot dot dot, which is approximately 2.53 radians. All right? If you have come this far, then I know that you are the real seekers and you are here to learn and get some knowledge. So there was so much in the first bullet and I had to go over each of the terms one by one. But if you get tired in the later videos as well, you can pause it and save it to watch it later. Don't miss out on anything because everything that you see on this channel is very authentic and very up to date and to the point according to the exam, right? So that's why I share those bullets and give you every detail from the syllabus document, right? So the final thing I want to talk about, but after this I will end the video, is known as conjugate. What is the conjugate of a complex number? Come on, guys, write it again, box it somewhere. So if you have a complex number, let's say a plus ib, the conjugate has different notations. When I was a student, we used to use this z bar, like a bar on the top. But now the CIs use this notation, z steric, which is the conjugate. How do you write a conjugate? Just change the sign of the imaginary part. You get it? Like a plus ib. What's the imaginary part sign? Positive. Make it, switch it to negative. Example. If you have u equals to 1 plus 3 iota, its conjugate is going to be 1 minus 3 iota. Or if you have w equals to minus root 3 minus I, then w steric is going to be minus root 3 a plus I. You get it? Change the sign not of the real part, but just of the imaginary part. Now, you might be wondering, what's the point of doing this, changing the sign of the imaginary part? So I'm going to show you the geometrical significance of complex number and its conjugate. Let's take this first example. U is a 1, 3, and U steric is a 1, negative 3 on the Argand diagram. What do you observe? Every complex number and its conjugate are the reflections of each other in the real axis. I know it's too much to digest, but let's write it. U and U star. Oh, sorry about that. U star are reflections in the real axis. All right, that's it for today, students. There's plenty more to come in my next videos. This is a huge topic, but in every Pure Mathematics 3, this comprises of like somewhere from 6 onward to 10 marks. So you get a huge question on this topic. Stay tuned for more useful videos. Over and out.